Hello everyone, myself Mrugendra Bhojraj Poddar, Assistant Professor, Department of Pharmaceutics at Shri Vile Parle Loni Mandal, Institute of Pharmacy, Dhule, affiliated under Dr. Babasaheb Ambedkar Technological University, Lonere, District, Raigad. In this video, I am going to discuss about size reduction. Disclaimer: this presentation is made for education purpose only and not meant for any commercial interest. The information provided in presentation by presenter is taken from his own personal experience and understanding and from the references quoted at the presentation. Learning objectives. After completion of video, the student should able to learn introduction of size reduction. In that, the definition of size reduction, different objectives of size reduction, advantages and disadvantages of size reduction. Second, mechanism of size reduction. Different mechanism involved in size reduction, that is by which mode the actual size reductions will take place. And third, laws governing in size reduction, that is theory involved in size reduction. Before starting the size reduction, there is a reflection spot. Just identify the pictures mentioned here. Picture A indicates as mixer. Picture B indicates as chopper. And picture C will indicates as mortar pestle. Now take a pause of video and think about this picture, which is used in our kitchen in our day-to-day life. From pictures, we get little bit idea about size reduction. Now we'll discuss about the size reduction. First, introduction of size reduction. Size reduction is a process of reducing large solid unit masses into small unit masses or fine particles. Because the pharmaceutical powders are polydispersed in nature, so they forms the difficulties in the production of dosage forms. Particle of monocytes may be ideal for pharmaceutical purposes. In engineering, the size reduction process is also termed as comminution, diminution or pulverization. Size reduction is nothing but the method or process in which the larger particle will convert into the smaller one, called as size reduction. Next, objectives of size reduction. There are different objectives or aim of size reduction. First, to facilitate the drying. Drying of granular mass can be rapid and effective if the size of granules is small and uniform. Such techniques are used in production of tablet. As size reduction increases, the surface area will also increases, and as surface area increases, the rate of drying will also increases. Second, to increase the surface area. As I tell, as size reduction increases, the surface area will also increases. By taking one example of potato, when single potato will convert into the small pieces by cutting, then the surface area will be increases. Third, to improve the appearance. The physical appearance of ointment, paste, cream can be improved by reducing its particle size. Next, to enhance the extraction of active component. Smaller particles shows rapid penetrations into tissues or cells. So the extraction of active constituents become effective and complete. The time required for extraction can be shortened. For example, by taking the example of ginger, when we add a piece of ginger and a powder of ginger, so the extraction from the powder of ginger will take place maximum and faster. Next objective, to facilitate the mixing. Mixing of different ingredients can be effective if the particle size is uniform and small. Size reduction ensure these objectives. So after size reduction, proper mixing will take place. Next, to increase the therapeutic effectiveness. Due to the fine particles, uniform distribution of active ingredients will take place, and which shows maximum absorption of drug, which result to increase the therapeutic effectiveness. The dose of griseofulvin is reduced to half than of its original required. Next, reduction in bulk volume. Reduction in bulk volume, which facilitate the reducing the shipping charges due to the small particle size. And last objective, chemical reactivity of fine particles. Chemical reactivity of fine particles is greater than that of coarse particles. It will react early as compared to coarse particles. So these are the objectives of size reduction. Now we'll discuss about the advantages and disadvantages of size reduction. First, we discuss the advantages of size reduction. In that, first, uniform flow. Smaller particle size and control size distribution promote the flow of powder into the dice during compression of tablet, and same principles are used in case of the production of capsule. Second advantage, effective extraction of drug. Due to the smaller particles, which allows rapid penetrations into the cells or tissue, it shows extraction of active ingredients become effective and complete, as well as the time required for extraction can be shortened. Next, effective drying. Drying of granular mass can be rapid and effective if the size of granules is small and uniform. Such techniques are used in case of production of tablets. Next, content uniformity. After size reduction, the content of active ingredients in dosage form is uniform due to the size reduction. Next, improve dissolution rate. As size reductions will take place, the rate of dissolutions will also increases. If we compare, the rate of dissolution of powder is maximum as compared with tablet. Next, to improve the rate of absorption. Smaller the particle size, faster is the absorption because of to enhance the rate of dissolution, as we discussed earlier. Now we'll discuss about the disadvantages of size reduction. First, drug degradation. The drug decomposition or the drug degradation is possible due to the heat produced during milling. Some of the material having ability to reduce, to lose, to produce the heat during size reductions called as thermolyable substances. So thermolyable substances are most affected for drug degradations. That's why the chances of contaminations will be increases. Next, contaminations. During milling and grinding, the grinding surface wear off, the particles of which is present as impurities in the powder. Such type of mills should be avoided when the drug of high purity are required. Next, poor mixing. Normally, very small particles possess strong cohesive force. That's why the aggregation of particles is possible, and aggregation inhibits the effective blending of different additives. As increase in surface area may promote the absorption of air, which may inhibit the wettability of drug during the production. So that's why the chances of poor mixing after more size reduction. So these are nothing but the different disadvantages of size reduction. After that, we'll discuss about the mechanism of size reduction. There are basically four mechanisms of size reductions. Mechanism indicates as modes of size reductions, will indicates as how the actual size reductions will take place. There are four different modes to reduce the particle size. First is cutting, then impact, then compression, then attrition. We'll discuss one by one. First mechanism of size reduction is cutting. Cutting indicates as the material is cut by means of sharp blades or of knife. If some materials are fibrous in nature like a ginger, so we reduce the particle size with the help of sharp blades or sharp knife. Then and then we'll get the pieces of particles. The example of cutting is nothing but cutter mill. Second is compression. We reduce the particle size by application of force. In this method, the material is crushed by application of pressure. For example, mortar and pestle. When we convert the chalk into chalk powder by using mortar and pestles by applying force, that is the example of compression. Example is roller mill. Next, impact. In another language, it is called as hammering. This involves the use of hammers or bars at high speed. Impact is nothing but the bombarding of two particles with each other or bombarding of particles and walls of equipments will take place. That's why the size reductions will take place. That is called as impact, called as bombarding or hammering of particles, or either particles will interact between the moving hammers or moving bars at high speed. That's why the size reductions will take place by the mechanism of impact. And last mechanism is attrition. Attrition is nothing but breaking down of the material by rubbing action between the two surfaces. For example, when the two particles will interact with each other, due to the friction, the surface of that particular material will be released. That is removal of edges only of that particle due to the frictions or due to the rubbing actions. That mechanism is called as attrition. For example, fluid energy mill. The mechanism of size reduction may vary with nature of material. Therefore, each drugs may require a separate treatment. However, the general mechanism may be described in this figure. If you observe, there is a unmilled particle. As per Griffith theory, every particle having a flaws, either visible or microscopic flaws are there. After application of impact or stress on that particles, the flaws will develop to cracks. Then after application of stress, the cracks are visible. Further application of stress or impact, the smaller particles and additional surface to form cleavage of particles to smaller size of particles will form. In case of attrition, if it is unmilled particles, after attritions or after frictions, the edges will be break of that particular smaller particles and the size reductions will take place. So in case of cutting, we use sharp blades or knife to cut the particles. In case of impact, that is after application of force or stress, the cracks will form, and further application of impact or stress, the cleavage of particles and to form smaller size of particles. So the size reductions will take place. In case of attritions, when two particles will interact with each other, due to the frictions, the edges are break and form a smaller particles. And last, in case of compression, by application of force, the particle size reductions will take place, that is nothing but compression. Now we discuss about the laws governing in size reduction, that is the different theories involved in case of size reduction. When the various modes of stress are applied on a powder, then the particles get strained. This stress-strain relationship will observe in that graph. That linear portions will indicate as the Hooke's law. It states that the stress is proportional to the strain. As we apply the stress, the strain will form. Strain will generated in case of particles. And the slope of that linear portions represent that the Young's modules. It expresses the stiffness or softness in megapascals. If the force of impact, that is stress, does not exceed the elastic limits, the material is reversibly deformed. When the force is removed, the particles returns to its original condition. The elastic limit is called as yield value. There are different theories of size reductions. According to Griffith's theory, all solid contains flaws and microscopic cracks are there. A flaw is any structural weakness that may develop into the crack under the strain. Now, as per the Griffith's theory, the amount of force to be applied will depend on the crack length and focus of the stress at the atomic bond of the crack apex. As Griffiths explains, how many force is required to obtain a crack. Every unmilled particles having a crack, but when we apply the stress, then that visual cracks will form. So as per Griffiths, how many force is required will depend on the crack length and the atomic bond of the crack apex. The equation is T is equal to under root of y E upon C, where T is equal to tensile strength, y is equal to Young's modulus, E is equal to surface energy of the wall of crack, and C is equal to critical crack path required for fracture. Now, energy required for size reductions. Size reductions begins with opening of small flaws that we initially present. There are different energy required for actual size reductions. The energy may use in case of to increase the new surface area from flaws. When we apply the force, the size reductions will take place. That's why the surface area will increases. So energy required to increase the new surface area. And second, to initiate the flaws or cracks in the particles. This phenomenon is observed generally in fine particles. Most efficient mill will utilize less than 1% of energy in fracture particles or create the new surface. The rest of energy will require in case of elastic deformation of unfractured particles, transportation of materials within the milling chamber. After some energy will required during the frictions between the particles, and mills. Some energy required to create or to form the heat during grinding. Some energy required to produce vibrations as well as noise during actual size reductions will take place. So these are nothing but the energy input and utilizations are important factor to estimate the efficiency of mill for a given material. Now we'll discuss about the different laws involved in case of size reductions. There are three basic laws. First is Kick's law, second Rittinger's law, and third one is Bond's law. As per Kick's law, the statement is the energy required for size reduction is directly proportional to the ratio of initial size of particle to the final size of particles, that is d1 upon d2. As per Kick's, the energy required to break the particles will depends on particle size. If you observe particle size between two, initial particle size before size reduction and final particle size after size reductions. Before will convert into the after. That's why how many energy is required. So energy required for size reductions is directly proportional to the size of particles. So if you want fine particles, you require more energy. If you want micro fine particles, so you require more and more energy to reduce the particle size. So as per Kick's law, energy is directly proportional to the initial particle size to the final particle size. So the equation is E is equal to Ck in d1 upon d2. E indicates as the energy required per unit weight, while Ck is nothing but Kick's constant. D1 indicates as size of feed, that is initial particle size. Second, D2 indicates as final particle size, that is the size of discharge. Next law, Rittinger's law. The statements of Rittinger's law is nothing but the energy required for size reduction is directly proportional to the increase in surface area. See, in case of Kick's, if we apply the energy, then the size reductions will take place. How many energy is required to break the particles will depends on how many particle size we require. If we require coarse, if we require fine, if we require microfine, so depends on that. Depends on the requirement of particle size, energy is required in case of Kick's law. In case of Rittinger's law, the energy required for size reductions is directly proportional to the increase in surface area. As I tell, the size reductions will take place, the surface area will also increases. Here the comparison between two surface area before size reduction and surface area after size reductions. So energy required to create new surface area, energy required for size reductions is directly proportional to increase in surface area. The equation is E is equal to Kr in bracket Sn minus Si bracket complete. Here E is nothing but the net energy required per unit weight, while Si is nothing but initial surface area. Sn is nothing but final surface area or new surface area, and Kr is nothing but Rittinger's constant. So here energy required for size reductions is directly proportional with surface area. And in case of Bond's law, the statement is the energy required in crack propagations is proportional to the new crack length. Here the equation is E is equal to 2 kb in bracket 1 upon under root of dn minus 1 upon under root of di bracket complete. Here E is equal to energy required for size reductions, kb is nothing but again bond work index, di initial diameter of particles, and dn final diameter of particles, or before size reduction di diameter of particles before size reductions, dn diameter of particles after size reductions, right? So in case of Bond's law, here the comparison between energy required is related with diameter of particles before size reductions and after size reductions. We'll see the comparisons between three laws. What Kick law says? Kick law says energy required will depends on particle size. Okay, how many energy required will depends on particle size, initial particle size and final particle size. Here the relationship between size and energy. As energy increases, the size of particles will be decreases. As the energy will increases, the size of particles will be decreases in case of Kick's law. And when the Kick's law is used, if the particle size is more, then and then we use the Kick's law. If we saw that Rittinger's law, this law will depends on surface area. In case of Kick's law will depends on particle size, Rittinger's law will depends on surface area, and Bond's law will depends on particle diameter. Here the relationship between energy and size in case of Kick's law. As energy increases, the particle size will be decreases. In case of Rittinger's law, as energy increases, the surface area will also increases. And in case of Bond's law, here the relationship between energy and diameter. So if the energy is increases, the diameter of particles will be decreases. That is the difference between Kick's law, Rittinger's law and Bond's law. When Kick's law will use, if the particle size is more, then and then the Kick's law will use. If the initial particle size is smaller, then Rittinger's law will use. This is nothing but the comparison between the Kick's law, Rittinger's law and Bond's law. These are the some questions, listed questions related with that topic, like define size reductions, state and explain the objectives of size reductions, enlist and explain the different modes of size reduction, write the advantages and disadvantages of size reduction, describe the theories of size reduction. These are the references. Thank you so much.